Okay, so the next field of discussion in our linear algebra course is going to be that of having vector spaces. Now, vector spaces are very important, especially when we come to um, checking out different dimensions and things like that, especially in terms of linear independence and just finding out different spaces in which different numbers exist. So having a solid understanding of what a vector space is very important. So it is defined as, let V be a set of vectors and F be a field. Okay. So we're gonna be letting, so we're gonna be doing certain assumptions here. So we're letting V be a set of vectors. So by that it's gonna just be represented by V being a certain set of vectors S1, S2 up to Sn, and let F be a field. So if F is a field, remember it has certain conditions thereof, addition and multiplication, and remember those addition and multiplication cases have further subcases, being that of Kane and Kane D respectively. So we have those fields and set of vectors with elements of V denoted by lowercase letters. So we can denote vectors as being lowercase letters. It will simply be convention that we would do this, but there are many other notations in which vectors are used. Sometimes the tilde can be used, things like that. It may even be bolded, but in this case we would just want to represent it in our case, and we're going to be representing it as lowercase letters. And elements of F denoted by lower Greek letters, exactly the same thing, referred to as scalars. And this is a common occurrence, having our field F, elements in field F being scalars. That's going to be a common occurrence. It'll just be like saying, in a normal case, let a certain element be in R for whatever reason. In this case, we're going to be letting our scalars lie in the domain of F, whichever field we choose that to be. So F would just usually be a set of scalars in this case. And then suppose two operations exist in V, vector addition and scalar multiplication. Now the difference between a vector space and a field is very important, and it's what I've just been discussing right now. A field is going to be a set of scalars, and those scalars need to adhere to conditions of addition and multiplications, which in and of itself have their own conditions of that of Kane and Kane D. The same is going to be said for vector spaces. A vector space is going to be a set that holds the conditions of vector addition in this case and vector multiplication. Vector addition and scalar multiplication. That is, to each pair of vectors AB, there corresponds a vector A plus B, and to each pair alpha, A, where alpha is a scalar, as we have defined there, to be in our field, and A is a vector, there corresponds a vector alpha A. So, having a certain vector, having a certain vector set of vectors, each element in that vector set or in that vector space is going to have elements such that if we have a certain vector A and we have a certain scalar A, there's going to exist a certain vector that is a scalar multiple of A. Just like saying in our field F, we're going to have, let's take for example number 2. If we have number 2 there, then there must exist a number 4, which is basically 2 times 2, which is a multiple of that scalar. It's also going to have negative 2, which is an inverse of that scalar. So the same idea is going to hold here, where each element in that vector set is going to be comprised of elements that contain itself, if that makes sense. And the same conditions are going to be held for vector sets or sets of vectors. Associativity, so now the distinction between the field and the set of vectors is that the vectors need to be of the same order. That's basic matrix and vector addition, that they have to be the same order, or it doesn't make sense for them to be added. So they have to be the same order, even in terms of subtleties like multiplication and all of that, but they have to be the same order. So associativity, commutativity, and now just as we had the zero element being for addition, such that whenever its operation is used, it will give out exactly that. That's exactly what we're going to be having here. And that null element or neutral element is going to be denoted as theta. And that's just basically going to be a zero vector, because it's necessary for our vector space to have that. It's also going to have its inverse element. Now, not inverse in terms of its of it being a matrix. It's inverse in terms of addition. So given a vector A, its vector negative A must exist such that when they are added, it gives us the zero vector, which is theta. Associativity under multiplication for a vector space is just going to be a scalar adding into that vector, as it's denoted here. Any scalar alpha, open brackets, and then this multiplication here, which is beta A, is going to be associative, because those scalars themselves can multiply, and then it can multiply with the vector and it won't make any difference. It's also going to have its identity element for multiplication, just as fields did. And it's also going to have its definition under its distribution over addition. So basically all of the attributes of a field are that of a vector space, except vector spaces are vectors and fields are scalars.